So today I'm going to be talking about Hyperflow, a processor architecture for non-malleable timing-safe information flow security. So modern computing systems have become increasingly reliant on the hardware to provide a root of trust. So for example, ARM Trust Zone, Intel SGX, and IBM Secure Blue have all been released to reduce the software component of the trusted computing base. But as more of the TCB is pushed into hardware, it becomes increasingly important to ensure that the hardware does not enable vulnerabilities. However, processors are also complex and error-prone systems. For example, nearly every processor that's released is followed by an errata document that lists bugs found in the processor after it was released. And prior work has shown that errata documents can be successfully mined to find security vulnerabilities. And processors can also be difficult to patch after they're released because we can't change fabricated silicon. And sometimes security vulnerabilities can be fixed with firmware updates, but often firmware updates have performance penalties. And even if we know how to implement processors correctly, this is also not sufficient because not all designs or specifications ensure security. Previously, processor designers have not considered timing channels part of the threat model, but the recent devastating timing channel attacks such as Spectre, Meltdown, and Foreshadow show that this is a poor assumption. So we need to guarantee security at design time before the processor is released. Our approach to doing this is to provide information flow security down to the hardware implementation level. The Hyperflow architecture supports software-defined security policies involving both confidentiality and integrity, as well as mutually distrusting principles that need to communicate yet are mutually distrusting. These policies are enforced by the Hyperflow ISA, which represents policies with a novel Hypercube label model, which can both enforce arbitrary policies represented with the lattice model and is amenable to efficient implementations in hardware. But Hyperflow architecture, rather than enforcing noninterference strictly, Hyperflow also needs to allow policies which allow communication. To support this, Hyperflow also supports downgrading instructions, which support communication needed for inter-process communication and system calls, yet still provide assurance despite this communication. The microarchitecture which implements the ISA enforces these policies with a tagged architecture. By enforcing memory protection with information flow labels, this offers stronger assurance than providing access controls because information flow security is transitive. The microarchitecture is also implemented to ensure that the confidentiality aspect of these policies is not violated through timing channels. To ensure that we've implemented this microarchitecture securely, the implementation is also done in hardware description language for information flow security called Chisel flow. This ensures that the implementation implements this policy and is free of timing channels. So next I'll talk a bit about how policies are represented in the Hyperflow architecture. Policies in Hyperflow are represented by Hypercube labels. Our intuition is that, so we want to be able to support policies that have been used in recent operating systems and programming languages for information flow security. And while these label models differ, our intuition is that all of them can be represented by lattices. So our approach is to represent them with lattices over bit vectors. This works by representing each bit vector as a point in a hypercube. So roughly each bit vector is split into some number of dimensions, and one vector is ordered before another if the first vector is numerically less than the corresponding dimension in the other vector. The meets and joins are computed by taking the dimension-wise minimum and maximum. It's straightforward to check that this both supports partial orders and has lattice properties. So labels are also pairs of confidentiality and integrity vectors. The confidentiality components have the order just described, but the order is reversed for integrity. Separating policies into confidentiality and integrity components is important for enforcing decentralized information flow control policies and for constraining downgrades. So prior operating systems and languages for information flow security support decentralized information flow control policies. These policies allow parties to share information while still retaining authority over further release of that information. As a classic example, consider a user of a tax preparation service named Bob. Bob needs to send his data to the tax preparation service so that it can do computation on that data, but he doesn't trust the tax preparation service not to release this data further to some third party such as Alice. So these are useful application security policies, but you may be wondering why we would like to enforce these in hardware. Well, by enforcing these policies in hardware, we can reduce assurance higher up in the stack, and we can also enforce these policies we can also ensure that these policies do not violate confidentiality through timing channels because we have precise control over how state is manipulated at the microarchitectural level. So how do we enforce these policies? Well, at a high level, decentralized information flow control requires some authorization mechanism that controls declassification and endorsements. To do this, we adopt a recent proposal for securely controlling downgrades called non-malleable information flow control. This security property is decomposed into two other properties called robust declassification and transparent endorsement. For robust declassification, integrity is used for authorization. Principals are prevented from declassifying information unless they are trusted with respect to the information they intend to release. So, for example, Bob can declassify his own data, but Alice cannot. For transparent endorsements, confidentiality is used for authorization. So parties are required to be able to at least read the information that they're attempting to endorse. So Bob can endorse his own data, but Alice is prevented from tampering with Bob's data and then claiming that Bob wrote it. So next I'll talk about how these labels appear at the ISA level. The process label represents the greatest secrecy that the currently executing process can observe and the most trusted information that the process can influence. The process label is also used to constrain indirect flows, such as implicit flows that may leak information through control flow, as well as timing channels. There are also register labels which are associated with each of the general purpose registers in the architecture. These labels represent the secrecy and trustedness of the data stored in these registers. Similarly, memory labels represent the secrecy and trust of pages of memory. The memory labels are also used for authorizing reads and writes to memory. By relying on information flow security to protect memory access, we also offer stronger assurance than access controls because information flow is transitive. These policies are enforced by ensuring that certain preconditions are established before executing each instruction. The main purposes of these preconditions are to both enforce memory protection and to ensure that labels accurately represent the data that they protect. The preconditions depend on the type of instruction executed. For example, load instructions must ensure that the data that's stored in the register, that the data that's going to be stored in the register flows to the label of the destination register. They also require that the label of the memory page being loaded flows to the label of the process label so that we know the process has the right to access that data. So these preconditions ensure that the policy is enforced strictly, but non-interference is too restrictive because it prevents communication between different parties. So we need to be able to downgrade information to support inter-process communication and system calls. There are two forms of downgrading instructions in Hyperflow ISA. The first are instructions for downgrading values. So registers can be downgraded by decalreg and endoreg instructions that declassify and endorse the value stored in registers. These instructions take as arguments the register to be downgraded and the value of the confidentiality or integrity component of the label after the update. These instructions both require that the downgrade is done non-malleably. Similarly, there are downgrading loads and stores, which work just like normal loads and stores, but they are permitted as long as the load or store can be done non-malleably, rather than enforcing information flow strictly. There are also page granularity downgrades, which reduce the labels of pages, similarly to register downgrades, and they're useful for doing zero-copy IPC of large amounts of data. Aside from value downgrading instructions, we also need to be able to downgrade control flow. For example, in order to do a system call, we need to be able to transition from an untrusted context to a trusted one. So also, when we're executing in a secret context, we need to be able to execute public libraries. So we need to transition from a secret context to a public one. In Hyperflow, this is done by a call gate mechanism. Call gates tightly couple an entry point program counter value with some mechanism for protecting that that entry point. In Hyperflow, these are unique because because protection is done with information flow labels. A new call gate can be registered with a regel gate instruction. The regel gate instruction takes as arguments the program counter of the new call gate, as well as the label of the call gate. Before this instruction can be executed, we must establish that the label of the process executing the instruction flows to the label of the new call gate. This ensures that the process could have authored a call gate with this label. Call gates can be executed with lcall instructions. The lcall instruction atomically copies the program counter and label of the call gate into the program counter and process label registers. At the same time, this instruction also pushes the previous program counter value and label onto a hardware stack. We can return to the previous program counter value and label by executing an lret instruction, which pops this hardware stack. So the Hyperflow microarchitecture is also constructed to ensure that timing channels do not leak the confidentiality component of these policies. This is done by using the process label to constrain the timing information that can be observed by the executing process, as well as the state that the process can modify. So the process is shared over time the processor is shared over time by processes which have different process labels. When we move from a process label with a higher secrecy value to a lower one, the processor is becoming less secret. So we need to prevent previous state and in-flight transactions from violating timing channels. This is done by inserting no-ops and dummy transactions into pipelines such as instruction and data caches, as well as the pipeline cache before the switch to a lower PC value takes place. We also need to clear pending state, such as cached. We also need to clear old state, such as cached address translations in the TLP and page table walker, as well as the instruction and data caches. Aside from previous transactions and state causing timing channels, there are also multi-cycle execution units that have execution times that depend on particular data values. We also need to prevent the execution time for these execution units from causing timing channels. We take two approaches to addressing these kinds of timing channels. In the floating point unit, we constrain floating point operations from being done on arguments that have labels that do not flow to the process label. For the multiplier, we constrain the multiplication unit to always take the worst case time. There is a trade-off between these two approaches. The FPU has a more restrictive ISA, but the multiplier has worse performance. So this describes how the architecture can be constructed to prevent timing channels, but we also would like to make sure that we've eliminated all of the timing channels. This can be done by HDL level we do this by hardware description level information flow control. So processors are normally described with code just like a piece of software. So our approach is to take language-based techniques for information flow security and apply them to hardware description languages. In this approach, the code that describes the processor is annotated with security labels, a type system that ensures that the policies described by these labels are enforced. Once the type system deems that this hardware implementation secure, the designer can then proceed with a conventional synthesis tool flow. And HDL level information flow control has a number of advantages. First, the runtime overheads are negligible because enforcement is done primarily at design time. Second, the engineering effort is fairly small because the hardware designer doesn't need to write manual proofs. They only need to add the information flow labels and then amend the implementation to ensure that it enforces this policy. And finally, it offers formal guarantees, namely that well-typed hardware modules enforce some variant of non-interference. And because hardware description languages give a cycle-level description of the hardware, we can also ensure that we can also provide a timing-safe variant of information flow security. So Hyperflow is constructed in a new language a new hardware description language for information flow security called Chisel flow. Somewhat confusingly for this talk, there are also labels at the implementation level that describe the security policy of the implementation that are distinct from the labels at the ISA level. So in the code that implements the processor, labels are added to the variables in the code, and then the type system checks that this policy is enforced. The in order to support efficient hardware designs that can be shared by different parties over time, we use a dependent type system, which is checked statically through a static program analysis. Chisel flow is implemented by extending the Chisel embedded domain-specific language for hardware description language. The front end extends this Chisel library and supports describing these policies. Enforcement is done by extending the intermediate representation for Chisel, which is called Fertile, and we rely on the Z3 SMT solver for doing static program analysis. Chisel flow also offers support for heterogeneous labels and label inference for making it easier to check that the design is secure. We also proved that Chisel flow enforces timing-safe observational determinism aside from downgrades. This gives strong assurance that hardware implemented with Chisel flow is secure and free of timing channels. The type rules for downgrades in Chisel flow also closely follow those of the type system used to study the security property non-malleable information flow control. The implementation of Hyperflow also type checks with Chisel flow with the use of some downgrades. The downgrades are all deemed non-malleable by the type system, and most of these downgrades are used to implement the ISA level downgrading instructions. Hyperflow is prototyped by extending the RISC-V rocket chip processor. This processor has a number of microarchitectural features which have also been absent in a number of previous information flow processors which have been statically secured with information flow. We also synthesized Hyperflow for a Zinc 7000 FPGA target. The synthesis results show a roughly 16.5% utilization overhead compared to a comparable architecture without these security features. The clock frequency is also unchanged. The cycles per instruction, we also executed a number of RISC-V benchmarks and show that the cycle per instruction overhead has a 12% geometric mean. To study the usability of the Hyperflow ISA, we also implemented a version of the tax preparation program where Bob and the tax preparer are both implemented as communicating processes. This example shows that Hyperflow is capable of representing decentralized information flow control policies, and that it can support communication via interprocess communication and system calls. I'll talk briefly about some closely related work. So there are also processors for dynamic information flow tracking, such as DIFC and Raksha. These similarly have tagged registers and memory locations and propagate these tags as the processor executes. These enforce integrity only and not confidentiality, and they also ensure these tags are updated strictly and do not support downgrades. There are also other processors that can enforce information flow security, such as Loki and Pump. However, these processors do not handle timing channels. There are also other hardware description languages for information flow security, for example, Kyson, Sapper, and SecVerilog. Chisel flow closely follows the design of SecVerilog, but it is also the first embedded domain-specific language for hardware descriptions that supports information flow control, and it also adds label inference and better support for heterogeneous labels. There are also other processor implementations that have been secured with information flow, such as gate-level information tracking, and as well as a number of processors which were implemented to study these languages. However, these support only simple two-domain security policies and do not support downgrades, and either do not support downgrades or offer no assurance when downgrades are used. In conclusion, Hyperflow is a hardware architecture for enforcing complex application security policies in a timing-safe way. A number of key contributions are that it supports decentralized information flow control policies, which are represented with the novel Hypercube label representation. We also support necessary information release to support interprocess communication and system calls. We also provide assurance in the implementation by implementing Hyperflow in a hardware description language for information flow security. The results suggest that the Hyperflow ISA is expressive and that the implementation has modest hardware overheads. Thanks.